Imagine looking up at the night sky, where every star that twinkles in the sky is a galaxy that is far away. These galaxies are home to billions of stars, countless planets, and potentially even life forms. They resemble islands in an endless ocean. However, what would happen if several of these islands vanished overnight? This is a true and confusing mystery facing modern astronomy, not a storyline from a science fiction book. Galaxies are enormous structures that don't simply disappear into thin air. Their absence is an indication that the cosmos is going through a significant and maybe catastrophic event. Comprehending this celestial occurrence is not just a scholarly endeavor. It contains the secret to understanding the fundamental structure of our cosmos. Understanding the processes governing cosmic evolution, the life cycle of celestial bodies, and the ultimate fate of the universe itself may be possible through the study of galaxy death. Understanding the size and complexity of galaxies is necessary to fully appreciate the enormity of this mystery. The cosmos is made up of these enormous clusters of stars, gas, and dark matter that are held together by gravity. Every galaxy is a dynamic object that is always changing and reacting with its surroundings. Their structure and behavior can undergo drastic alterations as a result of their ability to merge, collide, and occasionally even consume one another. Even with these extreme occurrences, the complete vanishing or dying of a galaxy is a very distinct and much more perplexing phenomenon. It is impossible to exaggerate the significance of comprehending galaxy deaths. Galaxies are not solitary objects. Rather, they are part of a web of cosmic relationships that both affect and are affected by the universe. A galaxy's demise might have far-reaching effects on the greater cosmic structure in addition to its immediate environs. Scientists intend to learn more about the underlying mechanisms guiding the universe's evolution by examining these occurrences. Our investigation has several goals in mind. Our first goal is to examine the ideas and theories that are now being used to try and explain why galaxies die. Do these deaths stem from external causes like interactions with other galaxies or the effect of dark matter? Or are they the product of internal processes like the exhaustion of star-forming material? Knowing the causes underlying galaxy death will help us better understand the intricate interactions between the forces that govern our universe. Secondly, we aim to investigate the techniques and tools that astronomers employ to investigate these celestial occurrences. More windows into the cosmos have been made possible by contemporary telescopes and observational methods, enabling scientists to delve deeper and more precisely than in the past. We can appreciate the state-of-the-art instruments that are contributing to the resolution of this cosmic riddle by taking a close look at the most recent findings and technological developments. Lastly, we will explore the wider ramifications of galactic deaths. What do these occurrences teach us about the universe's past, present, and future? What impact do they have on our knowledge of cosmology and the possibility of extragalactic life? We may situate the phenomena of galaxy death within the broader framework of cosmic evolution and our place in the cosmos by thinking about these issues. We cordially ask you to accompany us as we delve into this cosmic wonder as we set off on our exploration. With the help of the spirit of exploration and the light of scientific inquiry, we shall together navigate through the darkness. In the process, we aim to learn more about the enormous, enigmatic, and breathtaking cosmos we live in, as well as the mysteries surrounding fading galaxies. Join us as we explore the universe in an effort to solve the mystery of galaxy deaths. This expedition aims to solve one of the most intriguing mysteries in the cosmos through a journey of amazement, discovery, and deep understanding. The basic components of the universe are galaxies, which are enormous collections of stars, gas, dust, and dark matter held together by gravity. Billion or trillions of stars, nebulae, star clusters, and different interstellar media can all be found in a galaxy. Every galaxy is an isolated system made up of stars that develop in dense gas and dust regions, complete their life cycles, and frequently explode as supernovae to release materials back into space and fuel the formation of new stars. The cyclical process of star production and annihilation is essential to the billion-year history of galaxies. A supermassive black hole, whose mass can range from millions to billions of times that of the Sun, is located at the center of most galaxies. These black holes are essential to the dynamics and evolution of the galaxies they inhabit. affecting the galactic matter distribution and star formation rates. The complex motion of stars and other objects in a galaxy is controlled by the interaction of dark matter distribution, gravity, and other astrophysical phenomena. Galaxies exhibit a wide range of morphologies and dimensions, but can be broadly categorized into three primary types: spiral, elliptical, and irregular. Each kind possesses unique properties and evolutionary histories. Perhaps the most spectacular galaxies in terms of visual impact are spirals, like our own Milky Way. They have a core bulge of older stars and a flat revolving disk filled with stars, gas, and dust. From the central bulge, spiral arms travel around the galaxy and frequently contain starburst regions, areas where star creation is active. These arms are usually rich in nebulae and young blazing stars. Density waves, which function as traffic jams and cause gas and dust to compress and start star formation as they travel across the galaxy, are responsible for maintaining the structure of spiral galaxies. The Milky Way is a prime example of the intricacy and beauty of these galaxies, with its central bar structure and conspicuous spiral arms. Elliptical galaxies lack the distinguishing structure found in spiral galaxies and range in shape from almost spherical to very elongated. They have relatively little gas and dust in older, colder stars, which suggests that there hasn't been much star formation. Elliptical galaxies appear smooth and featureless because their stars circle in random directions. These galaxies are believed to be the product of galaxy mergers, in which the gravitational pull of merging galaxies causes structural disruption and intense star creation, which eventually settles into an elliptical shape. Because of this, elliptical galaxies are frequently located in areas of the cosmos that are densely populated, like galaxy clusters. The systematic division of spiral and elliptical galaxies into categories is broken by irregular galaxies. They have no distinct shape and frequently have a disorganized look with no discernible structure or form. Gas and dust abundance in irregular galaxies suggests that star formation is still occurring. They can be seen both isolated and inside larger galaxy clusters, and they are typically smaller than spiral and elliptical galaxies. These galaxies' asymmetrical characteristics are frequently the consequence of collisions with other galaxies or gravitational interactions, which cause structural distortion and spurts of star creation. In spite of their seemingly chaotic appearance, irregular galaxies are essential to our comprehension of the processes that propel star creation and the evolution of galaxies. Galaxies are found inside the cosmic web, a huge linked network of cosmic formations. They are not isolated islands in the universe. This web connects clusters and superclusters of galaxies with filaments of gas and dark matter spanning billions of light years. Galaxies interact, combine, and change within this web, changing the structure and dynamics of the cosmos on a massive scale. Galaxies are more than just groups of stars in the cosmos. They are the places where stars are formed, grow, and die, and they are essential to the process of cosmic development. Supernovae and stellar winds release elements created in star cores into space, enriching the interstellar medium and supplying the building blocks for planets, new stars, and possibly life itself. Galaxies can be used as cosmic laboratories to study the interactions between dark matter, gravity, and other astrophysical processes. Astronomers can learn more about the properties of dark matter, the actions of supermassive black holes, and the processes guiding star formation and galaxy evolution by studying and analyzing galaxies. Galaxies are also crucial to our comprehension of the universe's large-scale structure. Their mobility and dispersion offer hints about the forces forming the underlying cosmic structure. Astronomers can map the distribution of dark matter, trace the history of cosmic expansion, and test cosmological ideas by studying galaxies and their interactions. Galaxies are essentially the universe's engines, propelling the cycle of matter and energy that shapes the universe. Their research offers a more comprehensive picture of the past, present, and future of the universe, in addition to illuminating the minute characteristics of particular galaxies. This fundamental understanding of galaxies, their types, and their roles in the universe will direct our investigation and spur our search for solutions as we delve deeper into the enigma of galactic deaths. The stoppage of star creation is one of the most definitive indicators that a galaxy is dying. Star nurseries are areas of dense gas and dust in a thriving galaxy where new stars are formed. A plentiful supply of cool gas that can collapse under its own gravity to produce stars is necessary for this process to occur. But in a dying galaxy, this star-forming activity decreases dramatically or stops completely. There are various reasons why star creation may stop. One theory is that there is no more material in the galaxy to produce stars. The gas that drives star formation can run out over billions of years. Gas from the galaxy can also be expelled by supernovae and stellar winds from already existing stars, which reduces the amount of material accessible for the formation of new stars. The galaxy's gas heating up could be another issue. A supermassive black hole or active galactic nucleus, AGN, in the heart of the galaxy may occasionally emit energy that heats the surrounding gas to such high temperatures that it is unable to cool down and create stars. This phenomenon, called AGN feedback, has the ability to essentially stop star formation, causing the galaxy to progressively disappear. Star creation stops, and the galaxy gets fainter. A galaxy that is still undergoing star formation seems bright and brilliant, because young, hot stars are significantly brighter than older stars. The youthful stars eventually fade off and are replaced by older, colder stars that emit less light when star formation ceases. As a result, the brightness of the galaxy gradually decreases. Through the measurement of galaxy luminosity over time, astronomers are able to see this fading. A drop in brightness may be a sign of a diminishing population of stars and an absence of fresh star formation. Furthermore, a galaxy's hue can alter as it fades. Because of the abundance of young, massive stars, galaxies that are actively generating stars frequently have a blue appearance. The galaxy's color changes to red as a result of these stars dying and no new stars forming. Older, colder stars predominate. Telescopes that monitor light at various wavelengths can detect this shift in color and luminosity. Through the comparison of data made at different wavelengths, astronomers are able to construct a comprehensive picture of the star formation history and current status of the galaxy. Galaxies experience profound structural and compositional alterations throughout their demise. The decline in the galaxy's gas and dust content is one of the most obvious changes. The interstellar medium gets scarce if there aren't any new stars to replenish these components. Supernova, or the activity of the center supermassive black hole, can ionize and eject the remaining gas. Interactions with neighboring galaxies frequently have an impact on the structural modifications. Galaxies may merge and interact gravitationally with nearby galaxies in dense environments like galaxy clusters. These interactions have the power to remove gas and dust, change the galaxy's internal dynamics, and distort its shape. Such interactions, for instance, might cause a spiral galaxy to lose its recognizable arms and take on an increasingly elliptical or irregular appearance. Furthermore, there may be signs of supermassive black hole activity in the center parts of dying galaxies. A black hole may occasionally become active, absorbing matter and releasing strong energy jets that may have an effect on the galaxy nearby. This process can accelerate the galaxy's demise by releasing more gas and preventing star formation. Important insights into the mechanisms of galaxy death can be gained from observations of the structure and composition of galaxies. The Hubble Space Telescope and other high-resolution imaging instruments enable astronomers to examine the intricate morphology of galaxies. Spectroscopic observations are useful in determining the quantity and condition of gas and dust within galaxies by analyzing the light from these objects to determine their composition. Through the study of these visible indicators, such as decreased star formation, fading and dimming, and structural and compositional changes, astronomers are able to piece together the life cycle of galaxies and the processes in which they end. These observations are critical not just for comprehending particular galaxies, but also for obtaining a more comprehensive knowledge of the universe's evolution. The complex interactions and balances that control the course of cosmic development are made clearer by studying dying galaxies. Our knowledge of galaxy death will grow as we use ever more sophisticated telescopes and observational methods to study the cosmos, offering new perspectives on the existence and ultimate fate of these amazing cosmic formations. Even while the cause of the death of entire galaxies is still unknown, astronomers are gradually solving the puzzle by paying attention to these visible indicators. One of the most spectacular phenomena in the cosmos is a galactic collision, sometimes referred to as a galactic merger. The gravitational forces that result from galaxy collisions can cause dramatic structural changes, spur star formation bursts, and ultimately cause one or both merging galaxies to die. These collisions are not uncommon. In fact, they are an essential part of the history of galaxies, altering them and causing large-scale cosmic change. When two or more galaxies approach one another and their gravitational fields interact, a galaxy merger takes place. These interactions move the galaxies toward one another throughout time, resulting in collisions and the formation of a single bigger galaxy. The masses, velocities, and trajectories of the galaxies involved affect the process, which can take hundreds of millions to billions of years. The stars, gas, and dark matter of the merging galaxies interact intricately. Because of their great distances from one another, individual stars in galaxies seldom collide, despite the seeming violence of these events. Nonetheless, the dynamics and architecture of the galaxies are significantly altered by the gravitational forces. The first pass, when the galaxies initially approach closely, is the beginning phase of the interaction. Long tidal tails and gas and star bridges can be produced by the tidal forces that arise during this phase, stretching and distorting the galaxies. The galaxies may continue to orbit one another after this first meeting, progressively losing energy and getting closer until they eventually combine to form a single object. A galactic collision can have a significant effect on the composition and rate of star creation in the galaxies involved. First, the gravitational perturbations may compress the gas clouds in the galaxies, leading to powerful flares of star formation. The star populations of the galaxies can momentarily be revitalized by these starburst phases, which can produce new stars at rates substantially higher than those of isolated galaxies. But when the merger intensifies, the intense interactions may cause material to be ejected into interstellar space or gas and dust to be stripped away by tidal forces. In the end, star formation decreases as a result of this loss of star-forming material. The galaxy's capacity to support its stellar population declines in the absence of new gas, paving the way for its ultimate demise. An elliptical galaxy is usually formed in the last phases of a galactic merger. Whether spiral or irregular, the initial structures of colliding galaxies are frequently destroyed, and their stars settle into a more sporadic spheroidal distribution. The recently created elliptical galaxy has little to no continuing star formation and a smooth, featureless appearance. The galaxy seems faded and darkened because the surviving stars are usually older, colder, and redder. Galactic mergers can cause structural alterations, as well as ignite the central supermassive black holes within the merging galaxies. Supermassive black holes may merge and grow bigger and more massive when the galaxy's centers converge. Strong active galactic nuclei, AGN, can be produced by this mechanism, in which the black hole accretes surrounding material and releases enormous amounts of energy. Any residual star-forming material may be prevented from cooling and condensing into new stars by the intense heat and gas expulsion caused by AGN. A galaxy merger's final result is determined by a number of variables, including as the relative sizes and kinds of the galaxies involved. Elliptical galaxies are more likely to develop and undergo major structural changes as a result of collisions between galaxies of similar sizes. Though they may not totally upend the larger galaxy's structure, minor mergers, in which a smaller galaxy merges with a larger one, can nevertheless alter star formation and cause material to be redistributed. Interstellar collisions serve as a reminder of the universe's dynamic and ever-changing character. They show how galaxies change over time due to interactions and mergers, and they emphasize the role that gravity plays in forming cosmic architecture. These occurrences can be disastrous for the individual galaxies involved, but they also act as a catalyst for the redistribution of matter and energy throughout the universe and the formation of new, larger galaxies. Deciphering galactic collisions is essential to understanding galaxy demise. Astronomers can learn more about the mechanisms that deprive galaxies of their star-forming material, cause activity spikes, and ultimately cause the galaxies to collapse by examining these cosmic interactions. We get closer to understanding the intricate life cycles of galaxies and the factors guiding their evolution as we keep tracking and modeling these occurrences. Supermassive black holes, which have masses ranging from millions to billions of times that of the Sun, are at the center of nearly all massive galaxies. These black holes have a profound effect on the galaxies they inhabit, especially when they are in an active state called an active galactic nucleus, AGN. When material from its surroundings is accreted or drawn in by a supermassive black hole, an AGN happens. This material warms up and releases massive amounts of energy across the electromagnetic spectrum, from radio waves to X-rays, as it spirals into the black hole. An AGN's existence can have a significant impact on a galaxy. The accreting black hole's energy output has the ability to propel strong winds and jets that travel throughout the galaxy and have an effect on the interstellar medium. The surrounding gas may get heated by these outflows, which could stop it from cooling and condensing to generate new stars. This process can successfully suppress star formation and accelerate the demise of the galaxy. It is referred to as AGN feedback. Two primary mechanisms underlie AGN feedback: the radiative, also known as quasar mode, and the kinetic, also known as radio mode. When the black hole is in the kinetic mode, it produces relativistic jets that can drive gas out of the galaxy, while in the radiative mode, the energy released by the accretion disk around it ionizes and warms the gas. Both processes have the potential to deplete the galaxy's star-forming material, which would reduce the rate at which new stars are formed and ultimately speed up the galaxy's demise. The brightest and most severe type of AGN activity are called quasars. The supermassive black holes accreting material at astronomically high rates are the source of power for these far-off, brilliant objects. A quasar can produce more energy than all of the stars in its home galaxy put together. Although quasars generate light in all electromagnetic spectrums, their strong X-ray and ultraviolet emissions make them stand out in particular. The host galaxies of quasars can be significantly affected by the energy they discharge. Strong winds that expel gas from the galaxy can be generated by the quasar's radiation pressure. The interstellar medium, the raw material required for star formation, may be removed from the galaxy by this process. The galaxy's capacity to create new stars is severely limited in the absence of this gas, which causes the population of stars and luminosity to gradually decrease. Quasar observations show that their influence extends well beyond their immediate surroundings. A quasar can radiate winds and radiation that are tens or even hundreds of thousands of light-years away, impacting not only the host galaxy, but also the environment around it. This broad impact emphasizes how important quasars are in determining how galaxies evolve and ultimately end. Due to their AGN activity, supermassive black holes have the ability to significantly alter galaxies. Black holes remove gas from galaxies through a variety of intricate and efficient methods. The evacuation of gas through energetic fluxes is one main method. These outflows may originate as jets propelled by the black hole's surrounding magnetic fields, or as winds propelled by the accretion disk's strong radiation. Winds propelled by radiation can travel at speeds of thousands of kilometers per second, removing enormous volumes of gas from the galaxy's core. The gas may be forced farther by these winds, where it has a lower chance of cooling and becoming stars. The galaxy's total luminosity and star formation rate decrease as a result of the loss of this gas, which results in fewer new stars being produced. Jet-driven outflows can also be very influential. These are frequently linked to radio-loud AGN. By heating the gas and preventing it from cooling and compressing to form stars, the jets have the ability to introduce energy into the interstellar medium of the galaxy. The gas can sometimes be physically driven out of the galaxy by the jets, which further reduces the supply of material that can create stars. A phenomenon called AGN feedback heating can also result from the AGN heating of gas. In this scenario, the AGN's energy causes the surrounding gas to heat up to such a high degree that it becomes thermally stable, which prevents it from cooling down and condensing into molecular clouds, which are the locations of star formation. The production of new stars can be successfully stopped by this heating effect, which can spread throughout the galaxy. The quantity of cool gas accessible for star formation is significantly decreased as a result of these processes taken together. This gas loss eventually causes less new stars to emerge, which causes the galaxy to fade and finally die. Hence, supermassive black holes' influence on AGN activity plays a crucial role in galaxies' lifespan, determining their final course and evolution. One of the universe's most enigmatic and elusive elements is dark matter. Since it is invisible and only discernible by its gravitational effects on visible stuff, it cannot emit, absorb, or reflect light. Dark matter, which makes up roughly 27% of the universe's mass energy content despite its elusiveness, is essential to the development and evolution of galaxies. A number of hypotheses try to explain the relationship between dark matter and galaxy death. Dark matter halos are the wide, generally spherical distributions of dark matter that surround galaxies. According to one well-known explanation, these distributions are crucial for the stability and development of galaxies. These halos draw in and hold on to the gas required for star formation, providing the gravitational framework that allows galaxies to form and flourish. On the other hand, interactions between visible and dark matter may play a role in galaxy death as galaxies evolve. The gravitational pull of dark matter halos on galaxy mergers is one way this happens. The interaction of two galaxies' dark matter halos can produce tidal forces that can displace gas and stars from the colliding galaxies. Stellar activity may decrease as a result of this process, often referred to as tidal stripping, which might exhaust the gas reservoirs required for star formation. The function of dark matter in galaxy clusters is the subject of another theory. The dark matter halos of individual galaxies can overlap and interact in these dense environments, causing gas to be stripped off galaxies as they pass through the gravitational potential of the cluster. Ram pressure stripping is the process by which a galaxy loses gas and, as a result, its capacity to create new stars when it travels quickly through the hot, dense intracluster medium. Moreover, dark matter's effect on the universe's large-scale structure may have an indirect bearing on galaxy death. The immense network of filaments and voids that defines the large-scale structure of the cosmos is shaped by the distribution of dark matter. Within this web, galaxies grow and develop, and their interactions with the surrounding dark matter can have an impact on the rates of star formation and the general evolution of the galaxy. Through its ability to accelerate the expansion of the universe, dark energy plays a fundamentally different role than dark matter in the formation and evolution of galaxies through gravitational interactions. About 68% of the mass energy content of the universe is made up of the enigmatic component known as dark energy. Although its existence is still one of the great mysteries of cosmology, its consequences on the expansion of the universe are significant. Dark energy is the primary force influencing the large-scale dynamics of the cosmos, as was discovered in the late 1990s with the discovery of the universe's accelerating expansion. The ramifications of this rapid expansion for cosmic structure evolution and galaxy demise are profound. The growing isolation of galaxies is one of the main effects of dark energy. Galaxies separate from one another as the cosmos grows faster and faster. The distance between galaxies is widened by this expansion, which lowers the probability of mergers and galactic contacts. This isolation will intensify in the far future, eventually resulting in a cosmos where huge, empty voids divide galaxies. Because dark energy isolates a galaxy, there is less fresh gas available for star formation, which has an impact on galaxy evolution. Galaxies regularly collided and merged in the early cosmos, resulting in a steady supply of gas and spurring star formation bursts. However, these interactions become less frequent as galaxies are driven farther away by dark energy. Galaxies exhaust their internal gas stores and star production decreases in the absence of gas input from other sources. Furthermore, the general structure of galaxy clusters is impacted by the faster expansion caused by dark energy. The gravitational force within clusters becomes less strong as the cosmos expands, making the clusters less closely bound. This phenomenon may result in the dispersion of galaxies and gas inside clusters, hence exacerbating the decrease in star formation. The eventual demise of galaxies and the fate of the cosmos are both impacted by dark energy. The universe will someday go through a phase known as the Big Freeze or heat death, in which galaxies drift so far apart that interactions and star formation completely stop. This is assuming the current rate of accelerated expansion continues. The universe will eventually become cold, dark, and almost empty as the surviving stars progressively fade away. The precise form of dark energy is yet unclear, but it is evident that it plays a part in galaxy death and cosmic expansion. Dark energy separates galaxies, restricts their capacity to take in new gas, and modifies the large-scale structure of the universe by causing the universe to expand faster than before. Determining the ultimate fate of galaxies and the cosmos at large requires an understanding of dark energy. Large quantities of hot gas, substantial dark matter, and hundreds to thousands of galaxies make up galaxy clusters, the biggest gravitationally bound formations in the universe. The evolution and ultimate demise of the galaxies housed within these clusters are significantly influenced by their environment. High-density environments and strong gravitational interactions around galaxy clusters produce special circumstances that can accelerate the death of galaxies. Gravitational interactions are one of the main ways that galaxy clusters affect the galaxies that make up their cluster. Galaxies encounter close encounters and gravitational perturbations on a regular basis as they navigate the environment of dense clusters. The gravitational attraction of neighboring galaxies or the cluster as a whole can drag away the outer layers of a galaxy's stars and gas, a process known as tidal stripping. This can result from these interactions. The galaxy's capacity to create new stars is diminished as a result of this process, which also causes a decrease in star formation. Galaxies can cause dynamical friction in addition to tidal stripping. This happens when a galaxy passes through the dense environment of the cluster, generating a wake of gas and dark matter that pulls the galaxy toward itself. The galaxy may lose speed due to this drag effect and spiral inward into the center of the cluster, where interactions with neighboring galaxies and the intra-cluster medium, ICM, intensify even further. Large elliptical galaxies and an abundance of hot gas frequently dominate these center regions, further depriving infalling galaxies of their star-forming material. The space between galaxies in a cluster is filled with a hot, diffuse plasma known as the intra-cluster medium, ICM. It has a temperature of millions of degrees Kelvin and is mostly made up of ionized hydrogen and helium. Ram pressure stripping is the process by which galaxies pass through the ICM. The pressure from the hot gas pushes out the gas within the galaxy. Because galaxies move through the ICM at such high velocities, ram pressure stripping works especially well in cluster environments. The ICM exerts a force that can force a galaxy's gas out of its gravitational well when it passes through this heated plasma. The observed tails of this stripped gas show that star-forming material is still being removed from the galaxy. The ability of the galaxy to create new stars is significantly reduced as a result of the gas lost due to ram pressure stripping. The galaxy gradually loses luminosity as a result of a decrease in star formation rates brought on by the gas loss. In the dense cores of galaxy clusters, where the ICM density and pressure are maximum, this process is very prevalent. The residual gas in galaxies can also be heated by the ICM, which keeps it from cooling and forming new stars. This gas thermalization contributes to the general cooling of galaxies within clusters and further suppresses star formation. Galaxies and clusters experience an accelerated mortality due to the combined effects of gas heating, ram pressure stripping, and tidal stripping, which produce an unfavorable environment for star formation. Able 1656, sometimes referred to as the Coma cluster, is one of the universe's most extensively researched galaxy clusters. Situated in the Coma Berenices constellation, some 320 million light-years distant, this huge cluster is home to more than 1,000 known galaxies. The Coma cluster is characterized by a compact core, an enormous intra-cluster medium, and a massive population of elliptical and lenticular galaxies. Astronomical research has focused on the Coma cluster because of its close proximity and wide variety of galaxy types. It offers a unique laboratory for researching the mechanisms influencing the death and evolution of galaxies in a cluster setting. The Coma cluster observations have provided important new information on the mechanisms behind gas stripping, galaxy interactions, and the general dynamics of galaxy clusters. One of the best examples of how the cluster environment can cause galaxy death is the Coma cluster. Many wavelengths of observations such as radio, X-ray, and optical have shown various important processes operating within the cluster. Ram pressure stripping is a common occurrence in the Coma cluster, which is one of its most notable characteristics. Long ionized gas tails that follow many of the cluster's galaxies are a sign of the ICM's continuous gas removal process. These tails are especially noticeable in spiral galaxies that are losing star-forming gas and changing into lenticular or elliptical galaxies. Galaxies in the Coma cluster. Experiencing ram pressure stripping have substantially lower star formation rates than isolated galaxies or those in less packed settings, according to high-resolution imaging and spectroscopy data. The damaged galaxies gradually fade and get redder as a result of the loss of gas, which also reduces the production of new stars. These galaxies change over time from gas-poor, quiet ellipticals or lenticulars to active star-forming systems. In addition, tidal interactions are common in the Coma cluster. Numerous galaxies show signs of prior near contacts and gravitational interactions with other cluster members, such as deformed forms, tidal tails, and bridges of stars and gas. The shifting of gas and stars caused by these tidal interactions accelerates the demise of galaxies by further diminishing the material needed to produce stars. Apart from tidal interactions and ram pressure stripping, the dense core of the Coma cluster is important for galaxy evolution. Strong gas heating and strong stripping are more likely to occur in galaxies in this setting due to the high ICM density and the gravitational potential of the cluster core. Massive elliptical galaxies, which frequently exhibit signs of previous mergers and interactions, predominate in this center area. The quenching of star production is further facilitated by the supermassive black holes located in the nuclei of these giant galaxies. The accretion of material onto these black holes causes active galactic nuclei (AGN) activity, which can produce strong jets and outflows that heat the surrounding plasma and prevent it from cooling. This AGN feedback process also suppresses star formation, which helps quench the cluster's galaxy population as a whole. Another well-known galaxy cluster is the Virgo cluster, which is situated in the constellation Virgo and is roughly 54 million light-years away. With over 1,500 member galaxies, it is the nearest major galaxy cluster to the Milky Way, making it an important area to study galaxy evolution and interactions. In comparison to the Coma cluster, the Virgo cluster is less dense and more irregular, covering an area of roughly 2.2 million light-years. There is a mixture of spiral, elliptical, and irregular galaxies in the Virgo cluster, which is dominated by two large elliptical galaxies, M87 and M49. The cluster's diversity of galaxy types offers a fertile field for studying the different mechanisms influencing galaxy death and transformation. Because of the cluster's closeness to Earth, in-depth measurements at many wavelengths may be made, offering valuable information about how the environment affects the galaxies that make up the cluster. A good illustration of how the cluster environment might impact galaxy evolution is the Virgo cluster. The cluster's galaxies undergo a number of important processes that have been seen to play a role in their final transition and demise. Ram pressure stripping is an important process in the Virgo cluster, just like in the Coma cluster. Because they move through the intra-cluster medium, ICM, many galaxies in the Virgo cluster show evidence of gas stripping. Long, narrow gas tails have been seen trailing behind multiple galaxies in observations made with the Hubble Space Telescope and other instruments. These tails show that the galaxies are losing interstellar medium as they pass through the cluster. Ram pressure stripping is still evident in the spiral galaxy NGC 4522, which is one well-studied example. NGC 4522's core regions are intact, while the outside gas disk is being torn away, according to high-resolution imagery. The galaxy's star creation is impacted by this selective stripping, which causes the inner regions to continue forming stars at a slower rate, while the outer regions see a decline in new star formation. The Virgo cluster also has a lot of tidal interactions. Numerous galaxies have deformed forms, tidal tails, and star streams as evidence of previous gravitational contacts. These characteristics are proof of the gravitational pull that neighboring galaxies have on the afflicted galaxies, which can alter their dynamics and structure. For instance, the warped structure and extended tidal tails of the spiral galaxy NGC 4438 in the Virgo cluster point to a previous close encounter with another galaxy. The galaxy's star-forming material may be reduced by these interactions, which also contribute to the galaxy's slow fading. Active galactic nuclei, AGN, are found in the center parts of several Virgo cluster galaxies. These are places where supermassive black holes accrete material and release intense jets and outflows. The large elliptical galaxy M87 is one noteworthy example, with a noticeable jet flowing from its center black hole. Star formation can be suppressed by AGN activity's ability to heat the surrounding gas and keep it from cooling and condensing into new stars. M87 and other AGN-hosting galaxies in the Virgo cluster are seen to provide evidence of the influence of AGN feedback on galaxy evolution. AGN's jets and outflows have the power to force gas out of the galaxy or heat it to extremely high temperatures, which prevents star formation and speeds up the galaxy's general decline. Galactic cannibalism is the process by which larger galaxies grow by accreting smaller galaxies in crowded cluster environments such as the Virgo cluster. Massive elliptical galaxies may grow as a result of this mechanism, whereas smaller satellite galaxies may disappear. Virgo cluster observations show several examples of smaller galaxies being accreted by larger ones, which causes the smaller galaxies to lose stars and gas and eventually merge with the larger ones. Our knowledge of galaxy evolution and the mechanisms leading to galactic death has been transformed by the development of modern telescopes. Astronomers can now examine the structures, relationships, and star formation processes of galaxies and clusters in unprecedented detail thanks to high-resolution images provided by the Hubble Space Telescope, HST. The fine features of galaxy form and the influence of environmental influences on galaxy evolution have been made visible by Hubble's deep field views. The most sophisticated space observatory to date is the James Webb Space Telescope, JWST, which will launch in 2021. Because of JWST's ability to see in the infrared, it can see through gas and dust to see the early phases of galaxy formation and evolution. The study of star formation rates, the characteristics of the interstellar medium, and the interactions between galaxies in clusters like as Virgo and Coma are made possible by its strong instruments. A vital tool for researching galaxies and their surroundings is spectroscopy. A galaxy's composition, velocity, temperature, and other physical characteristics can be ascertained by astronomers by examining the light that the galaxy emits or absorbs. Detailed information regarding the chemical composition of galaxies, the existence of active galactic nuclei, and the star and gas velocities inside galaxies may be obtained by spectroscopic measurements. Millions of galaxies have been mapped across the sky by spectroscopic surveys like the Sloan Digital Sky Survey, SDSS, offering a thorough understanding of the large-scale structure of the cosmos and the distribution of galaxies within clusters. These surveys have demonstrated the frequency of AGN activity, gas stripping, and other processes involved in galaxy death. Combining spectroscopy with high-resolution images enables astronomers to build intricate models of galaxy history and interactions. The visible proof of tidal tails, deformed forms, and other characteristics suggestive of gravitational interactions and gas stripping is provided by imaging from telescopes such as Hubble and JWST. Spectroscopic information completes these pictures by offering the physical background required to comprehend the underlying mechanisms. Understanding galactic interactions and the mechanisms leading to galaxy demise depends heavily on theoretical models and simulations. Astronomers may investigate the dynamics of galaxy collisions, mergers, and other interactions over billions of years by building intricate computational simulations. The intricate gravitational processes at work and their consequences for galaxy structure, star formation, and gas dispersion are clarified by these models. The Illustris and Illustris TNG simulations, which model the formation and evolution of galaxies within a huge cosmic volume, are among the most significant simulation efforts. The impacts of dark energy, dark matter, star formation, supernova feedback, and AGN feedback are all included in these models. Through testing ideas about galaxy evolution and fine-tuning models to better reflect the real universe, scientists may compare the outcomes of these simulations with observational evidence. Galaxy interaction simulations demonstrate the long-term effects of ram pressure stripping, mergers, and tidal pressures on galaxies. They provide insight into the intricate physics of how gas is extracted from clustered galaxies, how star formation is suppressed, and how galaxies can change in type. These understandings are crucial for deciphering observational data and comprehending the larger scheme of galaxy evolution. Astronomers can also forecast how galaxies and the universe will behave in the future according to theoretical models. For example, calculations indicate that in approximately 4.5 billion years, the Milky Way will crash and merge with the Andromeda Galaxy. The structure of both galaxies will be significantly altered by this upcoming collision, commonly known as the Milkomeda event, and a new elliptical galaxy will be formed. The long-term impacts of dark energy on galaxy clusters are also predicted by simulations. Galaxies within clusters will get more and more isolated as dark energy propels the universe's accelerating expansion. It is predicted that galaxy clusters will break up over trillions of years, leaving individual galaxies as isolated islands in a vast emptiness. A decrease in star formation and the ultimate fading of galaxies will result from this isolation, which will restrict interactions and mergers. Astronomers can gain a better understanding of the final destiny of galaxies and the cosmos by examining these predictions. These models offer a framework for deciphering recent discoveries and projecting cosmic occurrences in the future, which aids in piecing together the universe's long-term development. New insights into the mechanisms of galaxy death and transition have been obtained through recent investigations. A noteworthy finding relates to the function of cold gas in the evolution of galaxies. Atacama Large Millimeter-Submillimeter Array (ALMA) observations have shown that substantial amounts of cold gas can be found in galaxies that appear dead, meaning they are no longer forming new stars. This discovery contradicts earlier theories and indicates that other elements, including the availability of molecular clouds and the impact of AGN feedback, are also important in initiating star formation. The observation of jellyfish galaxies in clusters is another significant finding. These galaxies have young stars and lengthy trailing streamers of gas that resemble the tentacles of jellyfish. Based on observations, these structures are the result of extreme ram pressure stripping that occurs as the galaxies pass through the ICM. Researchers can gain a detailed understanding of the dynamics underlying gas stripping and star formation quenching by examining jellyfish galaxies. Currently, a large number of studies are being conducted to learn more about the causes and effects of galactic death. When it fully launches in the near future, the Large Synoptic Survey Telescope, LSST, will perform an unparalleled sky survey, offering in-depth studies of millions of galaxies. With the help of this survey, scientists will be able to examine galaxy evolution on a large scale and spot patterns and trends that point to the mechanisms underlying galaxy death. The Event Horizon Telescope, EHT, another important endeavor, seeks to take high-resolution pictures of supermassive black holes. Through monitoring black hole environments across galaxies, the EHT will yield important information on AGN activity and how it affects galaxy evolution. These findings will contribute to our understanding of how AGN feedback suppresses star formation and causes galaxy death. A key event in cosmic history that has shaped the universe's structure and evolution is the death of galaxies. The death of a galaxy affects the dynamics of galaxy clusters overall, as well as the development of new galaxies by redistributing stars and gas. Comprehending the mechanisms underlying galaxy death facilitates researchers in piecing together the life cycles of galaxies and the forces propelling their evolutionary processes. Understanding the mechanisms of galaxy death also contributes to our comprehension of the universe's large-scale structure. Astronomers can learn more about the distribution of matter and the role played by dark matter and dark energy in the evolution of the universe by examining the changes and fading of galaxies throughout time. Researchers can forecast how galaxies will behave in the future by comprehending the mechanisms that cause galaxy death. Galaxies will grow more remote from one another as dark energy powers the universe's accelerating expansion, which will reduce interactions and mergers. Because of this isolation, there won't be as much available gas for star formation, which will lead galaxies to fade and become inactive systems. These discoveries aid in the prediction of the universe's long-term evolution and the final destiny of galaxies. Through a combination of observation and forward modeling, astronomers are able to construct a detailed model of the universe's evolution over billions of years. The study of galaxy evolution and death has been transformed by the introduction of sophisticated observational instruments. Unprecedented views of galaxies and their environs have been made possible by instruments like the Hubble Space Telescope, the James Webb Space Telescope, and the Atacama Large Millimeter-Submillimeter Array. These views have revealed the minute intricacies of galaxy interactions and changes. Future developments in observational technologies should improve our comprehension of galactic death even more. Even more in-depth surveys of galaxies throughout the electromagnetic spectrum will be possible thanks to initiatives like the Square Kilometre Array, SKA, and the Extremely Large Telescope, ELT. With the use of these tools, scientists will be able to more precisely examine the characteristics of galaxies and their surroundings, leading to the discovery of novel mechanisms underlying the evolution of galaxies. There is tremendous potential for fresh findings in the field of galaxy evolution as technology develops. Researchers will be able to delve deeper into the cosmos and examine galaxies at earlier phases of their evolution, as well as the causes underlying their alterations, thanks to improved observational techniques. These findings will contribute to our knowledge of galaxy death and offer new perspectives on the basic mechanisms governing the universe. A wide range of phenomena, including galactic collisions, supermassive black hole activity, interactions between dark matter and dark energy, and environmental conditions inside galaxy clusters, are studied in the intricate and multidimensional discipline of galaxy death research. Important insights into these processes have been gained by observational methods and theoretical models, which have shown the complex dynamics of galaxy evolution and alteration. Further investigation on galaxy death is crucial to improve our knowledge of the evolution of the cosmos. Through examining the factors leading to galactic death, scientists can learn more about the larger systems governing the structure and dynamics of the universe. New insights into the life cycles of galaxies and the processes that affect them are expected to be uncovered by ongoing observational programs and technological advancements. Astrophysics continues to find the enigma of galaxy deaths to be an interesting and important field of study. We are getting closer to understanding the causes of galaxies' extinction as we investigate the cosmos with ever more sophisticated instruments and methods. These discoveries pique our interest in the enormous, dynamic, and always changing universe we live in, while also expanding our knowledge of the cosmos.